Alright, so for our example of a linear time algorithm, I'm going to work with the in function that we've seen previously. So public, and by previously I meant when I was going over the homework. So public static e boolean alright, gotta give it a name, in, which is going to take in a list of elements and an item, and it's going to search the list for that item. Okay? And what we'll do is we write a pretty simple for loop. So for each item, for each thing in the list, right? For each thing in the list, if item dot equals the list, not the list, thing, then we found the thing, return true. Else, we didn't find it, return false. Right? Okay. So what we're going to do here is that we are going to build this list, and we're going to see how a couple of just some subtleties of big O notation here for this linear time algorithm. The first thing I'm going to do is that I'm going to stop just adding all these numbers in, just all sorts of numbers in, which is instead I'm going to go ahead and create a random list, right? Because I want to deal with what might be called a real world example. Random rand to create a new random number generator, right? All right, and so now rather than adding in a rather than adding 0 at index 0, 1 at index 1, 2 at index 2, instead I'm going to give it a next int. I'm going to give it a number between, let's say, let's go ahead and 1 and 20,000, right? We'll go ahead and actually give it between, we'll go ahead and grab next int. And that will give us any random integer from 1 billion, from negative 2 billion to 2 billion. Now, for purposes that I'll show you later, what I'm going to do is I'm going to make this positive. I'm going to do that, make that positive. That's what. So you probably haven't seen this before, right? But you know immediately what this means. That means make this negative, right? Flip the sign of that. And having a positive sign there, it's a unary operator, which means it just takes one operator. It has one operand, rather. That means it's just going to force the random number to be positive. So if it's negative, it's going to turn it positive. If it's positive, it's going to turn that positive, which means it stays positive, right? Okay. So no problems there making our list. And we got to now search that list for this item. Okay? Okay. So now we've got 10,000 items. So this actually doesn't take that long at all. Let's see. So we're going to say it's in the list. We're going to look for the number 13 in the list. And we run it. And it took 11 milliseconds. So we're going to move it up from 10,000 to 10 million. And see how much longer that takes. Took 95 milliseconds. Doesn't really seem to be that slow. Well, it doesn't really seem to be a linear algorithm. Like I said, I mean, it took a little longer, but not that much longer. I mean, 10,000 versus 10 million. Right? What about 100 million? Is that going to take much longer? I think it's just not too much longer. Well, actually, hold on a second. Should take about 8 seconds, perhaps. But first, it's got to make all the list, right? It's got to make all the items. So this was, yep. Oh, 532 milliseconds. So once we made the list, it took half a second. So I was completely off there. Okay. And part of the reason that I'm completely off on all these things is because this is such a quick operation for it to do, right? We're really good at just traversing through all these items and checking if stuff is equal. That's a really easy operation for the computer to do. So if you want to see how this is a linear algorithm, we actually need to slow it down. So we're going to use the trick we used earlier, right? And the trick is that I'm going to slow this down by what I'm going to do. I'm going to just simply do a system.out.print here. So I'm going to print out nothing, and I'm going to print out that for int I is equal to 0. I is less than 10,000, I plus plus. So I'm going to do this 10,000 times. Now the reason I'm doing this is just to slow this down so we get a better grasp of what's going on. I'm making my computer do a lot more heavy lifting in order to check an item. And as a result, I'm going to bring this back down to 10,000. Let's see. So now it actually takes some time for it to do. Print line statements for each of these guys. Takes a while now. Okay, let's go. Oh, so it took substantially longer for 10,000. It took me 15 seconds to do that check. So let's go ahead and lower the amount of work it has to do. Okay. Now it should be able to handle that. So, okay, running on 10,000 units takes about 1.8 seconds. Running on this algorithm on 1,000 units took 298. Now, it's also possible that there's some randomness, right? Like that. And why is that? Well, I'm generating random numbers, 1,000 of them. It's possible that one of them is 13. So that's part of the reason I force them positive. Okay. Now, when we analyze algorithms, part of what we need to do is we look at 3 different kinds of cases. We look at the best case, right? We look at the average case, or those are 3 cases to consider, and the worst case. All right. Now, the best case algorithm, we don't really pay attention to it when we're analyzing our algorithm that much. And why is that? Because the best case often relies on us getting lucky. For instance, what is the best case scenario for the for this algorithm, right? I'm searching through all the items. Best case scenario is what? The item is there and it's the first thing in the list. So we're done in no time whatsoever, right? That requires us getting lucky, and programmers are walking personifications of Murphy's Law. You're not going to get lucky. Okay? Best case scenarios will almost never happen, so we don't because that would require luck. So we're not going to bother with that. Okay, so instead, let's take a look at the worst case scenario, which is actually often the best thing to analyze, the best thing to plan for, right? If you plan for the worst, then we know what to expect. Okay, and the worst case scenario is that we search this list for an item and it isn't in there, right? So if we analyze the worst case, we know that our algorithm will never perform worse than this. So this algorithm, if it has n items in it, worst case scenario, we check n items to see if they exist, to see if the item is there. Worst case scenario, it's not there. Oh well. Okay, so that's the max. So worst case scenario, we check n items. The average case scenario, we check n over 2 items. Now, why is that? Well, we run this algorithm a bunch of times over a bunch of random numbers. Okay, sometimes the item that we're looking for is there at and we're going to assume it's there. Sometimes it's there at the beginning, closer to the beginning. Sometimes it's closer to the end. But if we run this a bunch of times, those cases will average out. It's going to be somewhere in the middle. So we look for, and we do we look for n over 2 items, which ends up being which is a linear relationship, right? So so for right now, we're going to look at the worst case scenario, which is that we're just going to not be able to. We're going to assume the item isn't there, right? So I forced all the items to be positive. and I'm going to look for a negative number. So this is a linear time algorithm, right? Because I'm checking to see each number in here, are you negative 13? So it takes 219 milliseconds, around. It's around 2 seconds to run this. So now this means, since it's a linear relationship, this means that there's a linear relation between the size of the list and how long this is going to take. So if I add a 0 here, if I multiply the amount of items I have to check by 10, then it should take possibly 10 times longer. So it took 200 milliseconds, and now we're at closer to 2 seconds, right? Right? And now I increase it by 10 again. So now we're talking about a runtime closer to 20 seconds, as you'll see here. Now, this is actually a very good runtime for us. This means that this, actually grows fairly slowly. It essentially means that if we add one more item to the list, then we have to do one more unit of work, which is, in this case, a unit being defined in this case of printing out 1,000 blank lines and then doing a equality check. So that's our linear algorithm. Okay. So next we're going to look at an example of a quadratic algorithm.